Okay, and meanwhile, for the offline viewers, let's have a closer look at this Blockly Games pond sample. So, how do we make a code for our duck which actually wins with the other ducks? That's a slightly more interesting problem there. And added benefit is that you will be able to see the JavaScript code corresponding to the blocks that you create. So okay, I'm gonna move okay. So let's see what happens if we don't have any code added. Oh, one of the ducks is going straight at us, and we see our life decrease, and there we die. So that's not very good. So let's see, what can we do? Let's see about making the duck a moving target rather than just a sitting duck. So to do that, I'd say let's go for a while loop. So let's have something like corresponding to like our update function in Unity, where something is happening every frame. This is pretty much the approach, the game loop that we are working with here. So, how do we make an infinite loop? Well, we only have while here, so we need to do a little trick. The while instruction only operates when this condition is true. So how about we make this always true? So under logic, I'm going to pick this true block, and anything that I put inside this while block is going to be executed forever. So the corresponding code looks like this in JavaScript. So what can we do? Well, we can, let's see at the instructions we have to work with. So in the pond documentation, we see that, okay, we have the definition of our angular coordinate system. So it starts here with 0 aiming to the right, and the angles grow counterclockwise through 90 pointing up and 180 pointing left, 270 pointing downward. We use this convention there when we fire our cannon. So our cannon function just fires a cannonball toward the specified angle and range. So let's maybe try this. Let's stick that cannon function. So every time that we can, we will fire the cannon at an angle of 0 and distance of 70. So this won't be super interesting. You see what happened there. So the duck is shooting into one particular direction, which is not very good, and it's not going to help us against those other evil ducks. So how about we will introduce a variable. So think about that little challenge that I gave you the last time to create a player health system where every time the player gets hit, the health decreases. So that would be just a public integer variable. In this case as well, we will use something for our duck direction. So let's say this is my let's say my private variable duck direction, which only the duck class knows about. So this duck direction variable is just initiated to 0 in this case. Let's initiate it just at the very beginning. And let us start with maybe -45. I think that should be a good direction. This should be actually the direction it's pointing in the beginning. So our initial direction -45. Is there a time function here to work with? Not really. No. That's okay. It's going to be very simplistic duck, but hopefully we can make it work. So remember our turtle example where we were able to move forward. In case of the duck, we have the swim function. The swim function just allows you to specify a direction in which to swim. I'm going to do something just temporarily. I'm going to put this into a function which I'm not going to use. This is just to kind of make it do nothing because I wanted to demonstrate something else. So what happens when I actually do swim 270? Even though it's only called once, the duck just swims forever and then crashes into the edge of the screen, so that's not very good. So the swim just initiates the swimming direction in this case, and the swimming just carries on concurrently. We're not updating position every time like we go through this while loop. So how about we actually modify this variable and change the direction all the time? We can do that. We'll just use the duck direction that we've created here, and then later on we're going to modify this duck direction variable. So here we're doing a plus equals, so we increment the duck direction by 1 every time. You can see that the code got generated, so this should do a basic circle, and it does. Okay, we have other functions like maybe random. So we could maybe actually play with a random trail for our duck. How about that? So I'm adding a random direction every time. Okay, so that creates a duck that's somewhat more working, still moving within a circle. Why? It's because this random function returns a value between 0 and 1, I believe. Yeah, that's it, between 0 and 1. So to change that, let's subtract half from this value. So I'm just taking this random value, subtracting half from it. So this would give me positive and negative values. So what's going to happen if I run this now? So the duck is veering a little bit, and now, okay, this is a problem because the health is decreasing. So not really that great of an idea. Let's multiply this so that we have a slightly more erratic. I'm gonna take this whole expression. Yep, and multiply it by 10, and let's see what that does to our duck. So I'm just exploring, being creative and seeing, okay, this is a kind of a jittery duck, but it is swimming somehow. So the problem is that the health starts to decrease, and eventually the duck dies. So to prevent that, I'm going to introduce a little bit of more complexity to my code. By the way, I'm kind of improvising, so you know, bear with me. This is, you know, I'm not really sure what I'm going to end up with at the end of this, but this is the approach that you know, you can take with playing with the procedural city as well as you try to get interesting effects. Some of the best, you know, results artistically and visually can come out of bugs or things you ran into completely by accident. So don't underestimate this kind of approach. It's very good to explore and you know, just try things and see what sticks. That's not a bad approach to getting interesting results at all. So let me create another variable, and I'll call it health. Okay, and inside our while loop, I'm gonna just use the pound health function. So I've just assigned health here. So this variable will be updated with the current value of health. So after I do my swim and so on, come back, how about I do a conditional, so logic if, and I'll stick it here, because what I want to happen is if we start hitting the wall or another duck, we need to change direction rapidly. So I'm going to create a logic expression here. So I have a not equal logic operator here. So let me stick our health variable, which we've assigned earlier. This is pseudocoding, so some of the things may be not working the way I'm assuming them to, so let's see. But that should be easy to remedy. So let's just experiment. So if the health is different than the value of health we obtained earlier, we'd like to do something else. So if that's the case, I'd like to increment the direction, the swimming direction. I'm going to do a 180. I think that's the safest. So let's see what's happening. Okay, this is not very good. Why did this get triggered? That's a bit unusual. Let's look in the documentation. RTFM. The health function returns the duck's current health level. Values are between 0, sunk, and 100 perfect. So advanced players may wish to store the health in a variable, that's what we did, that periodically check to see if the health has decreased, thus indicating that the duck is under attack. There's no way to repair health. Okay. So, plus 180. Yeah, that shouldn't have triggered. What happens if I change it now? Okay, that doesn't seem to work. Not a good approach, I think. Okay, I have to find a way to do it in the right moment, so okay. The function would be... Okay, I did something silly there. I shouldn't have named this variable the same. That's the problem, I think. So I'm going to delete this. Okay. Yeah, because health... Oh, okay. It's a health function. Okay. So no, that should be allowable. Okay, so we'll start with our health in the beginning. We assign this a health function. Okay. I think that's where I went wrong. I used the function, the variable instead of the function. So this should technically work. I'll just copy that. So my health variable now is assigned the value of current health. Okay, and we do all the other things. And now if present health is less than health, sorry, it's greater than health, so now this should be a correct approach. I think this should work. Let's see. Yep, so the duck hits the border and goes 180. Also hits another duck. Ah, we got stuck. Oh, but we escaped. So we're avoiding losing too much health by immediately changing direction when we hit something. Okay, so that's a start, but we still need to be more aware of our environment. So to do that, we have a function here called scan. The scan function activates the duck's radar. This function returns the range to the nearest opponent in the specified direction. So the angle is independent of the direction of the duck. Sunk opponents are not detected. If there's no opponent in that direction, then infinity is returned. Okay, so after we absorb this little bit of info, it's clear that we have to somehow control the scanning direction. So let's make a radar. I'm going to create a variable, a new variable, radar angle. Okay, I didn't use camel case, apologies, but let's not worry about this too much. And we'll start with, we'll start this value of whatever, 0. And then at each iteration, I'm going to increment this variable. So radar angle, I'm just gonna increment it by 1 every time. So in Unity, this would be every frame. Let's have a quick peek again in our code. So we already have started to accumulate this text. You can kind of see now this blocks way of creating your code is much more friendly than writing the text itself. But after you get more used to this, you can see that okay, this actually doesn't help you. Once you know what you're doing and you have been exposed to this type of programming, you won't need it so much. You might even think that this visual programming is a bit too tedious and cumbersome. But you can see that it's kind of a fun way to play and test and try out things and debug it real time. So I think it's definitely a good tool for those of you who still have problems creating more complex bits of code in C#. Start with this. Have a look at the JavaScript and then write your C# code based on this. And that's not a bad way to approach it. Okay, so let's have a look there at radar angle, which is changing, and we'd like to be scanning. So now we've done all this. Let's use the function scan. Scan returns the distance, right? So first of all, scan needs a function, needs an argument, the radar angle. Okay, so now let's say I'll create another variable to store the detected angle at which an enemy was detected. So enemy angle. So we scan radar angle and we assign this value. So this section in the code now is going to be our targeting, aiming. So enemy angle is scan radar angle. Radar angle is going to be incremented every frame. Okay, and oh, that's a mistake. I misunderstood the scan command. So the scan command will return a distance. So we need a logical expression there. So if, and remember what they said about the return of the result of the scan angle, scan function. It will be infinity if we didn't find anything. So if the scan radar angle, actually just to make it, yeah, let's store this result of the scan in another variable. So enemy distance. This is to prevent doing things too many times and running this scan function too many times. So variable enemy distance is equal scan radar angle. So now we use this enemy distance, check if it's math. Okay. Check if it's less than infinity. Actually, this does allow us to type infinite. This is a valid construct here. So if enemy distance is less than infinity, we know we hit something. So in this case, we set the enemy angle to whatever our aim angle is, the radar angle. So variables, radar angle. Well, let's see how that works. And right away, I think we can shoot. So Canon, variables, enemy angle, and distance. Distance is enemy distance. Cool. The JavaScript corresponding to this, something like this. Well, it doesn't look too bad. Let's try it. It's not shooting a lot. So why is that? Because you can have a look at the radar. The radar is moving very slow. So by the time it reaches a dock, it will start shooting, but by the time the dock might have moved. So I am going to increase the radar angle by some other number. So let's get creative. Maybe you want to make something a bit more unpredictable. How about let's have a look at the instructions. What else do we have to play with? Stop, get X, get Y, okay, speed. Okay, so we can query our speed. Get X, get Y. There's not really a way to find our own yeah, but we do have a variable dock direction. How about we just increment by that? That's going to be interesting. It might be a little bit unpredictable, but why not? So our radar angle now, every frame it will change by the direction. Let's see, we have something like a radar that's scanning left or right. Kind of interesting. Doesn't seem to be very effective though. It seems to be moving too fast. Okay, so math. Let's have some baseline value. Let's make it slower. So let's just multiply this by 0.2. So it's like dividing by 5. So let's see. Okay, so now our radar is doing all kinds of things depending on the current direction. It just makes things interesting and maybe unpredictable. You see that we have a a behavior a little bit like the behavior of the rook, which seems to be just always scanning on the horizontal and vertical. Okay, that's green rook down, that's green duck down, and we're still doing quite good on the health meter. Okay. Okay, and that's the game one. We are the best. And this is the JavaScript code. So now, you know, this would be quite similar now. I think it would probably almost look the same if we implemented in Unity and, you know, maybe used different functions for targeting. But we could actually think about having a bit of structure like this in our final project example for something that is having a little bit of perception and reacts to the environment. So, you know, that is a possible direction you can explore. Okay, so that's us. I think we have enough of ducks at the moment. Maybe another one that might be interesting is well, let me get you somewhat started on the turtle graphics. Let's see what we can do. Let me totally improvise this. I'm going to the level 10 again. Have a quick look. Okay, I can move forward, turn, set width of line, pen up, hide turtle, print something. Okay, that's interesting. Select the font for printing. Okay, so we can actually do some text. Color stuff. We can randomize color. We can color with specific red, green, blue components. We can blend between two colors. That's interesting. That's like interpolation, right? We have worked through mathf lerp or quaternion slurp. Color also has a lerp function, lerp method. So this is kind of an equivalent of a lerp for colors in this Blockly approach. So let's try something. I mentioned that some examples here actually deal with recursion. So because recursion lets you use very simple rules. Oh, this is interesting. That's a snowflake. Okay, recursion tree. So let's have a look what's happening here. To start with start level, let's see. Functions. I think this was written using JavaScript. We don't have insight into what's happening there, unfortunately. However, this tree sample is working. So let's reverse engineer what's happening there. I think that might be an interesting exercise for us. And also maybe it might give you ideas for procedurally generated flora or some other types of buildings or structures that you can have in your final project. So let's see what's happening. This is the main code. This is just the tree function. What's special about this tree function in this case is that you can see that the tree function is repeated only 5 times. What's happening if I run this only 1 time? So let's explore this. I want to understand what this code does, so I'm jumping right in and just playing around with the okay, so only once. I speeded it up to the maximum. Okay. Ratio. So let's see what variables are there and what can be working. We can see that it'll probably complete this whole first fractal tree. Repeat 1 times. Tree with size, tree size. Set tree size to 150. Okay, that probably just as the spatial extends. Yeah, I can make a smaller tree. Cool. Not really useful for us. What I'm interested in, how deep the iteration goes. So this is a if size, okay. Ratio, okay, set ratio to 0.6. What about okay, so this totally breaks it. 0.9. Okay, I just got a spiral out of this for free. 0.1 on the other hand. Okay, so this is where the complexity lies hidden. This ratio variable seems to determine how many times we go into the tree function. So you can see that there's only one call to this tree, so I can actually take it outside of the, just for clarity. This function tree is called with the parameter tree size set to 150, which is fine. There's a if size, okay, if size is less than 1 divided by ratio, then set color to red, otherwise set color to white. Well, you know what, I don't like any of this, so what I'm gonna do is just remove this whole section, and I'm gonna use a random color for this. So stick a random color. We need the set color function, and then random color is going to be just the parameter, and then do whatever they had before. Okay, so now I have a colorful tree. This ratio thing, still not really happy with it, so okay. So this ratio seems to actually define the fraction amount of how much shorter the next line is going to be from the current one. So we kind of deduce this by looking what it's doing. So if I make it 0.5, this means that the first line that the turtle draws is going to be twice as long as the next one. Okay, and now we have something like this. And this carries on until size is larger than a certain amount. So if I increase this, this will be much faster drawing tree. Okay, so this already helps me a lot. Let's see, do I want to go higher or lower? Oh, I think higher. Makes for a more interesting tree. Another thing you can see here is that the turn angle is deterministic. It's always 45 degrees. So what happens if we change or modify this this angle? We can play with that. That would be interesting. Could we randomize it? Well, that's interesting. Let's make it irregular. I don't like this way this tree, it doesn't look realistic. I'd like to have something more realistic. So I'm going to just a random fraction. So random fraction is going to give me a number from 0 to 1. So that's cool. And I'm going to multiply it by something. How about let's make a function for this, which returns a value. So let's say random range. Let's emulate this function that we use in Unity all the time. Create a variable. Well, actually, let's create it here for the function. So this is an input. Input 1, input 2. So I'd like to have a minimum value and a maximum value. And then I'm going to create a variable result. Set result 2. Okay, and now I have a minimum and maximum. I'd like to have something between them. Math. Do I have anything like this? Yeah, actually I do. Constrain between. Okay, constrain a number to be between specific limits, inclusive. Yeah. I think I'm going to go with simpler maths for this. So first of all, I'm going to subtract minimum from maximum. Okay, this gives me the range between minimum and maximum. And I'd like to multiply that by a random number, by that random fraction. What else do I need to do? Well, I need to add back the minimum value. Okay. So now I have a function and I can return the result. So this is going to be a handy, this is a little bit of a library that we can use. Okay, so I have a random range function now, and I'd like to use it here. So, functions, random range. So in this case, when I turn left by 45, I'd actually like to go between 40 and 50. So let's see what happens. Looks like a bug. Oh, right, okay, yes, this was a negative value there. What was it? 14, 15. I broke something. Oh yeah, I want to actually multiply this. Yeah, that's the problem. Okay, so we got something, but definitely it looked buggy. Okay, that's because this value now it's supposed to be, we're tracing back along the route, so to fix this I need to create a new variable. I'll just go temporary temp, and I'm gonna set temp to this, and I'm gonna use temp in here. But I'm also gonna use temp in there. And I'm kind of hopeful that this will fix something. Did I break something? If I say between 45 and 45, that should actually, yeah, that should be the same. Yeah, okay. Left by 10, right by, okay. Okay, that's it. So the way the turtle has to backtrack here. Okay, so that is now working correctly. Let's start slowly changing those values. So let's go between 43 and 45. Still seems okay. Let's increase this range. Okay, and let's make it a bit exaggerated now. 30 and 60. Let's see. Okay, it's a little bit broken. Well, I'm not going to go down this particular rabbit hole. Maybe this wasn't the best idea to experiment, so it's, sometimes it's good to pull the plug on an experiment. I'm not gonna try to fix this, but let's see what else we can do. So this is what's happening here, that the turtle is, let's slow down the execution and let's see what's happening. So the turtle goes forward, yeah, by size, then turns left by this angle and runs another tree. So as long as we're going left and running it's still running the tree, so we're not in the same, we're actually kind of keeping a stack of previous executions of the tree, and now this is starting to unfold. So this recursion executes until the size variable is less than 3 in this case. Because as you see that we run this tree with this size, and in the beginning, hold on, let's try quickly. Right. So the input, the starting point is, let's say this 0.6 for ratio. And then here, when we call the tree the next time, we call it with a size times ratio. So we're first running the tree with the length of 1, then we multiply this and run the tree. So this is a bit like running our tree tower block with a different position, and increasing the we're increasing that variable which tracked how many blocks we've already placed, so recursion level. So in this case, size would be equivalent of our recursion level. If you understand this setup, it's not that complex. Let me simplify it actually, so that things are a little bit clearer. Let me simplify it, and then just we'll skip the right leading branches. Okay, turn right, divide by 10. Okay, I'm gonna delete this, delete this. So this is going to be just partial. So this creates a bit of a spiral, right? The only thing is that on the way back by size, we missed some rotation back, so Okay, it's backtracking correctly now. Not necessarily ending in the same place because of our randomization. So this wasn't really a good place to put that random. So I'll finally and definitely abort this part of it, just for clarity for you. Okay, let's see if we can create a little more interesting spiral. We sure can by changing this angle. So how about we add another input argument to this function, which is the angle. Okay. So now we have to, when we call this tree the first time, we have to give it some initial angle. So let's try this angle of let's try angle of 80 degrees. Actually, no, let's try angle of 10 degrees. Let's just try a small angle. Tree size, let's set the tree size to a smaller number, a smaller tree, but the ratio I want it higher. And you start feeling what's going to happen. I want to have something more like a spiral. Okay, I'm getting there almost. I just have a bad starting point for this, so pen up, move backward by 90. I'll just delete this. I don't want this. I want it to start in the beginning. So actually I'm gonna rotate the turtle by 90, move forward by 190, and then turn it again left by 90. So I'm starting here, okay. Let's give it 100 to begin with. Okay, and there's a spiral, okay. Now we wouldn't need to have recursion for this. And this is probably not demonstrating very nicely in what's actually happening, because the turtle is now going in and then going back out of this. Because the function is calling itself, so let's abort this at 10. So this will stop going in earlier. However, I'd like to set color, okay, and down. So what happens if I didn't call this function within itself? If I remove the recursion, what is it actually going to do? Not much. Let's slow it down. Let's have a look. It rotates, okay, sets to 100, runs the thing, moves forward, left, okay, up, backwards, okay, and it ended up. I'd like to see where the turtle is. I'd like to see the backtracking, so I'm going to put the pen down, but I'm going to change the color while it does that. So let's say the blue color is going to be the backtrack. Don't see it. broke it. Oh, I didn't specify the angle. Oh, that's a bummer. So I'd like to turn left by the angle. And turn right by the angle after. Oh, okay, that's what happened there. Okay. And use the angle. Okay, that's a really big spiral that I just created, so let's start smaller. Let's start with a 20. Okay, so we did backtrack. So you can see that this part of the code, drawing in blue, didn't even get executed until the final tree got executed, which skipped this whole section. So otherwise it would be happening infinitely. So let's say I put a true here. What would that do? That would make this execute every time. So it will just infinitely go into an infinite spiral and keep going until the end of the world. Okay, so the tree function is calling the tree function, is calling the tree function, and it will just continue. So the reason why we have this terminating condition here, it is based on the size function, which is the parameter it's been called with, this particular instance of the tree, and this is the argument. So this ratio here defines the decreasing value of size as you go down along calling the tree function recursively. I think this is the most important bit to learn about this recursion, that you need to modify the input argument so that you can eventually cut off on some, there you go, we cut off on some kind of threshold and go back. Turn left by angles, backward by size, forward, down. Okay. Is there still a 10? Angle 10. So how about we do something funny with the angle as well? Right, we multiply the angle by the ratio as well. How about that? We need to use the and let's see what that does. Okay, this didn't change a lot, so I think in this case we'll have to change the ratio to something smaller. And the initial branch is going to be longer, right? Because they are going to get shorter. Okay, that didn't work great. Less than is greater than 0.01. Make very small values. I'm going to make this more lenient. So size has to be, as long as size is larger than 100, then we continue. So that should, okay, that still happened quite fast, because 0.5 is going to go down very fast. So 0.6 is going to give it a bit more chance. Okay. I'm gonna remove all this. So instead of multiplying the angle every time by the ratio, I divided it. So this will cause a slightly different effect. Maybe adding something would be more interesting. Let's see. Anyway, play with this until you're happy that you understand what's happening there. The main difficulty and the main challenge in this setup is that the function, it's calling itself, so it kind of like temporarily forgets execution of anything down from this call and has to take care of another version. Let's say, imagine that there's another function which is completely identical, only it's called tree2, and we would call that with a slightly modified arguments. So recursion pretends that we have an infinite series of these functions that we call recursively. Okay, I hope I didn't make it more complicated than it actually was, but I think after playing with this you'll get a better feeling for how the building blocks mechanism worked. Let's see what else we can do, just really quickly. Let's say remainders. Okay. Pi, sine. Okay, let's make a drunk turtle, just something fun to begin with. So loops, repeat while, yeah, logic true. So we'll make it infinite again. Turtle. We'll move it by some small steps. Color, set color to random. Okay, and here we'll use a sine function to turn by a certain amount. We'll use a sine function. Actually, oops. Okay, it's better maybe to use a for loop, then we have something to count and use a. No, let's skip for loops for now. Let's create a variable and call it counter. We'll pretend that we have a for loop. We'll just make it by hand. So variables, set counter to in the beginning. Let's set it to 0. And turn right by. So this counter is gonna be a bit like time, unity time or something. So. And then we use the counter as input to our sine function. Only sine function again will be between 1 and -1, so I'm going to multiply this to have a more obvious effect there. So hopefully we'll get a turtle that's weaving around a little bit. So multiply by 20. Okay, this happens too fast, so we actually need to. Oh no, it's the counter was never changed, so that's where I went wrong. So here set counter to math, and here we increment variables. Counter plus 1. Okay. That's a nice pattern. I didn't expect this, but it came out quite nice. Move forward, let's move it by 3. So we're kind of integrating the sine function and seeing where it goes. Okay. Okay, how about we vary the forward distance as well? by something which is sine or cosine based. I'm going to do the same kind of thing. I'm just plugging in different pieces of math to see what I end up with. Not the best results. Let's change it to cosine. The beauty of maths. Obviously this all really strongly depends on the initial values that you put in. So cool. Alright, thanks for today. See you next week. We'll talk about animations.